It's really surreal when you're talking about an asteroid sample return mission, 13 years ago, that we'd actually be at this point now. I had every confidence in the team that we get there, but your mind just isn't going there, right? You're just trying to get to launch, then you're just trying to get to the asteroid, then you're just trying to get through proximity operations and collect the sample. So you're taking a day at a time getting through operations. But yeah, now that we're here, ready to release the capsule, ready to finally collect it, culmination of all this work, decades of work, and really excited to see this thing get on the ground.
All we have left to do to deliver on our promise to the agency is get that sample safely back to the Earth, get it into our laboratories, and answer the fundamental questions about the formation of our solar system and why Earth is a habitable world.
3, 2, 1. And liftoff. Cyrus Craft.
The science speaks for itself. I mean, we're bringing back hundreds of grams of pristine sample from a body that hasn't been touched and is relatively unchanged since the beginnings of the very solar system. So the benefits to science are just astronomical. But the benefits to engineering, which is really what I'm interested in, is to me just as fascinating. It's like we're really pushing ourselves, the challenges, the things that we can do with the technology that we have. It's demonstrating our ability to deliver something from space to the ground safely and accurately. That's, to me, motivation enough to do these types of missions, well beyond even the science information that will gain from it, which is just invaluable to humanity.
And then really, the reason I answered the phone call, the reason I signed up for the mission, the reason I put in all of this hard work is finally going to come to pass. We're going to get pristine samples of carbonaceous asteroid in our laboratories and really go after the big question. Did these objects deliver the seeds of life to the Earth?
I'm not sure it's possible to identify one single person who will be the most stressed out. I'm sure that our principal investigator, Dante Loretta, will be very stressed, but also very, very excited, as this is the culmination for him of almost 20 years of work. But we have so many people on the team who are so invested in this and really, really care about the sample and who have been working on this mission for years and years and years. So I think we're all going to be a combination of very nervous and very excited.
Yeah, we're going into endgame here, after almost 20 years. It's been a long journey. I was invited to be part of the mission in February of 2004 when I was a young assistant professor, untenured, really trying to establish a research program, get used to teaching and committee work and all the things that you're expected to do, when I got a phone call from Dr. Mike Drake, the director of the Lunar and Planetary Laboratory.
I'm still very much personally guided by John Kennedy's comments when he directed the United States to send a man to the moon and return him safely to Earth by the end of the decade. In that same speech, he went on to say, we choose to do these things not because they are easy, but because they are hard. Well, spaceflight is hard, but we have, I think, such a good understanding of this mission that, in fact, we have no difficulty carrying it out. We have been very careful to assemble the best navigation team on the planet. And I can make that assertion with confidence.
And he invited me to be the deputy principal investigator on a proposal to NASA for an asteroid sample return mission. And, I kind of looked at the phone and I couldn't believe the words that were coming out of the earpiece, right? I was like, this is amazing. And also daunting, right? Because there's a lot of teams that are going after these kinds of missions, so it's a pretty risky venture, especially for an untenured young professor to buy in. This is an all-consuming effort, right? If you're going to win, this is what you're doing. You're writing that proposal, you're learning how a spacecraft operates, how you manage a giant NASA mission of this magnitude. But I couldn't say no. And the real reason was that my science demanded it, right? I've been studying meteorites for well over a decade with a key interest in what's called the exogenous delivery hypothesis. That is, did these carbon-rich asteroids deliver important organic compounds to the early Earth that triggered the origin of life? And as we studied meteorites in ever greater detail, we realized that we had just reached the limit because they're contaminated. And they're also biased. The atmosphere filters out the most fragile and friable material, leaving only the strongest to make it down to the surface of the Earth. So I knew if my science was going to progress, I had to sign on to an adventure like this. Plus, it was too cool to say no, right? I was like, how often do you get a phone call like that? And so, let's go. Let's get it done. And we wrote a proposal in 2004 and got rejected. And a proposal in 2005, and we made it to the next round, what's called Phase A in NASA's competition, and then got rejected. And then in 2008, the New Frontiers opportunity opened up. And I kind of knew at that moment, as soon as carbonaceous asteroid sample return was on the list, that it was ours to lose, because we had just gone through 4 years of intense design and development. And more importantly, the team had kind of crystallized. It became this well-oiled machine operating seamlessly. We were getting along, the ideas were flowing, and it just felt right. Like, okay, let's just go. And so we laid down, said, okay, we're gonna run hard and we're gonna run fast, and we're not gonna let any other team catch us. And so sure enough, in 2010, we made it to Phase A, and in May of 2011, we got that amazing phone call that we were gonna fly.
The last thing we really wanted was something that was going to excite the public. This mission is exciting.
It's hard to talk about Mike. You know, we lost him about 4 months after we won the contract. And he had been sick for a while up to that point, in and out of the hospital, had liver transplant surgery. He would be so proud of us right now. I mean, he was there to see us win. We were there at his house celebrating. He was extremely excited. He knew not only was this important for science, but for NASA, for the United States, and the University of Arizona, and the legacy that he had established as the director of that laboratory. So, you know, we honor him in many different ways. There's a plaque on the spacecraft to his memory.
8, 7, 6.
The rocket launch was dedicated to him, and there was a description on the Atlas V in his memory as well. And I think about him all the time. And I feel like he's there with me on the big moments, and he's really proud.
Touchdown declared.
All right.
Sampling is in progress.
So the sample return capsule is landing at the Utah Test and Training Range west of Salt Lake City, and this is an Air Force test range. It's a wide open area, basically a dried salt flat, dried lake bed. It's free of obstacles. It has lots of DoD tracking devices around there, and it's a controlled airspace. It's a great place to bring something back from space where you need a large landing footprint. Right now, we're only 60 days away from the sample landing. We're working on all of the final logistical details of getting all our people out to the site to do the recovery. We just completed a training last week. We're going to do another rehearsal in August, which will be our final rehearsal. A lot of moving parts right now.
So what we want to do is we're actually
When I found out I was going to be the ground recovery lead, I was very excited. It's rare that you get to be involved in some sort of a project that brings something back from space, and to be in a role where you get to oversee all of those operations and make sure that it happens without a hitch is just a really exciting opportunity. And we have to make sure that everybody is trained, that everybody agrees with the way that we're going to do things and is ready to go. And it's been fantastic because everybody's pulling in the same direction and we're ready to recover this.
So a very important requirement for OSIRIS-REx is to get the sample into a clean room as quickly as possible, because we're trying to maintain the pristine nature of the sample, make sure it doesn't get contaminated from stuff that's in the Earth's atmosphere or on the ground at UTTR. So the recovery team is designed to make that recovery happen as soon as possible. There's a couple of technicians from Lockheed Martin, there's a couple of curation specialists from the Johnson Space Center, and there's a couple members of our science team, and then there are 2 members of the Air Force that are our on-scene commanders that are helping us navigate the range. That team will fly out to the capsule landing site on 4 different helicopters, and they each have unique tasks of securing the capsule, making sure the area is safe, sampling, taking soil and air samples from around where the capsule landed to look for possible contaminants, and then get the capsule packaged up as quickly as possible to fly back via helicopter. So we're very concerned about the safety of the recovery team, and one of the possible things that could go wrong is if the batteries start on fire once the capsule lands. We don't expect this to happen, so one of the first things we're going to do when the capsule lands is one of the Lockheed Martin technicians will go up to it with a sensor to detect noxious gases that would be released if the battery were cooperating. And if we don't detect that, then we can proceed with the rest of the procedure. If we do, then we have to stand back and wait for the situation to clear.
So we fully expect when the sample return capsules hit the atmosphere that it will release the parachutes and descend slowly at that 11 miles per hour. But there is a chance that if something unexpected goes wrong, that the parachutes won't deploy.
Looks like we have a no-shoot, sir. Vector 200. Put it on your nose, 8 miles. Look for an impact.
DC, negative growth, negative shoot.
Copy. Receive the visual.
Impact at 5-8.
In that case, the sample return capsule will have a hard landing. It'll go very fast, it'll hit the ground, it'll likely rupture the sample return capsule. But that's a very low likelihood scenario. We fully expect that the sample return capsule, the parachutes will deploy, everything will work as expected, and we'll get that nice pristine sample in a very protected, enclosed sample return capsule.
So the spacecraft is approaching the Earth at a speed of over 27,000 miles per hour. It'll release the capsule at just the right moment to intersect the Earth's atmosphere. We only have one chance to do this. We can't, wave off and do it the next day. If there's bad weather, if there's a snowstorm at the UTR when we are getting ready to release the capsule, we will still release, and we will do our best to get to the capsule as quickly as possible. But this is truly a critical event. Everything has to happen on time in order to be successful here.
The team prepared for virtually every weather condition that we could think of. A number of our rehearsals we did in the rain. We also wanted to be prepared in case there was muddy conditions, so we actually built a custom mud pit and put the capsule inside of it and practiced recovering it. We also on every possible condition that we could see out here today.
Not an optimal scenario, but I think we can operate in it.
On September 24th,
allows us to get the capsule into the clean room just as quickly as possible, and ideally within 1 to 2 hours after landing.
We'll actually take off the heat shield and back shell and some other components for safety. And inside of that is what we call a sample canister. The sample return capsule is kind of like a nesting doll. We have these multiple layers of protection. And then that sample canister will have a nitrogen flow put on it, what we call a nitrogen purge. And with that nitrogen purge to protect the sample to keep any incursion of terrestrial atmosphere coming into that canister, it will be flown from Utah here to Houston, Texas. After which point we'll bring it into our building and get it into a glove box and open that canister up to see the tag SAM. And that'll be the first time we're seeing the tag SAM since it was stowed at Bennu.
On OSIRIS-REx, we have activities called Science Operational Proficiency Integrated Exercises, or SOPIs for short. These activities are fully integrated team events where we rehearse critical moments on the mission. In this case, we were looking at a simulant of the sample coming back from Asteroid Bennu, making sure we understand the different roles and responsibilities, team member communication, and our priorities and procedures. You can feel the stakes are rising as that sample gets closer and closer to the Earth. I was surprised by the pressure that the team was feeling. As the handlers were dealing with the simulant material, it was clear they understood the stakes, and my presence in the room was probably elevating the temperature, and they were a little bit concerned about that. So I was surprised that I need to do a better job as the leader, kind of damping down, lowering the temperature, making everybody understand how much we respect them, how well integrated this team is, and how valuable they are, so that they can do their job calmly and precisely, taking care to handle that sample really well. And everybody understands the science priorities and the process about how we're going to select individual stones and accumulations of fine particles to get out to the dozens of labs all around the world.
We have a number of different collections, actually. The first collection that NASA curates at Johnson Space Center was the Apollo collection, the rocks that the astronauts collected on the moon and brought back. So that was kind of the beginning of curation at NASA Johnson. The next collection was the Antarctic meteorites. And we also have had other sample return missions. Genesis, which was an array that captured basically elemental and particles coming off of the sun. The Stardust mission that flew behind a comet with aerogel. So all of those are different astromaterial samples, samples of material not from Earth, from space. I think actually the most difficult thing working in the glove box is basically you put your hands in, but you're only really usually up to at most here, so you lose all shoulder motion. And you'd be really surprised how much you do with your shoulders when you're using your arm. So you really can only work pretty immediately in front of you and a little to the side. You have such a lower range of motion than you normally do. So your colleague right next to you, you'll pass something to them that you maybe normally, when you're sitting at a conference room, you'd be able to reach yourself. But in the glove So all of this pre-planning we're doing is also so we can keep the sample as close as possible to the way it was when it was collected at the asteroid and when it returns to Earth, because those are the conditions that scientists are trying to study when they're studying this sample. So we're really lots and lots of careful control of any materials that might come in contact with the sample, both in construction of the lab, the glove boxes, what goes into the glove boxes, what immediately touches the sample, as well as our role in recovery in Utah. It's a lot of planning on the front side that we're really getting close to the finish line on. Also, afterwards, we continue to really be careful and super protective of that sample to preserve it for decades to come so it can continue to be studied as new instrumentation and scientific methods are developed.
On Earth, when you can bring the sample back, you can adapt to new information, you can adapt to new technologies, and you can use devices which are not small, but in fact enormous, the size of buildings, things that are actually larger than the launch pad, let alone the spacecraft. You can have the fussiest instruments that give you the best data that need babying because you have time and you have people who can make sure the instruments do what you need to get data that's just impossible to get in situ on a spacecraft at the object. So sample return gives you more power, more flexibility, and one of the wonderful things about it is it's available for the whole world who have new ideas and can express them by looking at the sample in their own way, even if they weren't part of the initial team. New analyses that have not yet been invented by people not yet born.
We're going back to the dawn of the solar system. We're looking for clues as to why Earth is a habitable world, this rare jewel in outer space that has oceans, it has a protective atmosphere. We think all of those materials were brought by these carbon-rich asteroids very early in our planetary system formation. And of course, the biggest question, the one that drives my scientific investigations, is the origin of life. What is life? How did it originate? And why was the Earth the place that it occurred? We believe that we're bringing back that kind of material. Literally maybe representatives of the seeds of life these asteroids delivered at the beginning of our planet that led to this amazing biosphere, biological evolution, and to us being here today to look back on that amazing history, to think about where did we come from?